One of the most common principles in both classical and modern physics is the principle of superposition. In most first-year classes, the principle of superposition is illustrated through the superposition of waves in space. Unlike particles which cannot occupy the same space, waves can pass directly through each other. When two waves occupy the same space, they will interfere. The displacement of the medium will be the sum of the displacement due to each individual wave. A simple way to illustrate this is to observe a triangular wave and a square wave traveling towards each other. When the two waves overlap, the resulting amplitude is the sum of the two component waves. In other words, the parts of the waves that are overlapping are added together. In more formal terms, the net amplitude caused by two or more waves traversing the same space is the sum of the amplitudes which would have been produced by the individual waves separately. We can explore the principle of superposition for waves using an Excel spreadsheet. First, we need to understand the relationship between the sinusoidal functions we've been dealing with and sinusoidal waves. Given a snapshot of a sinusoidal wave at 0 time, we can describe the displacement of the medium by a cosine function. Here, A represents the amplitude as before. Unlike the previous videos where we considered the period, we define a similar parameter called the wavelength lambda. The wavelength represents the distance the wave travels before it repeats itself, whereas the period was the amount of time before the cosine function repeated itself. This gives rise to an additional parameter called the wave number, k, which is equal to 2 times pi divided by the wavelength. You can think of it as a measure of how many wavelengths fit into 1 meter of space. As we mentioned earlier, discussing waves gives rise to another parameter we have not dealt with before called the wave speed. In general, the wave speed is a property of the medium the wave is traveling through. It is a constant if the medium does not change. For example, the speed of sound in air is smaller than the speed of sound in water. Simply, the wave speed describes how quickly the wave propagates through the medium. Given a sinusoidal wave with wave speed v, its evolution in time might look like the following. Remember, the wave extends well beyond the edges of our graph. We are just looking at a specific region in space, and each image is a snapshot at a given time. Let's explore this in Excel. For this demo, we will need to open a new spreadsheet. As before, we need to enable iterative calculation. Click on the Office button in the top left-hand corner. Click on Excel Options, and then click on Formulas. Here, choose Enable Iterative Calculation. Change the maximum iterations to 1 and the maximum change to 0.1. Hit OK, and we're ready to start our demo. We'll start by entering the titles of our columns. Here, we enter distance into B10, wave 1 into C10, and wave 2 into D10. As before, we will enter the amplitude, wavelength, wave number, and phase constant for both wave 1 and wave 2. In A1, enter amplitude 1. This corresponds to the amplitude of wave 1. In A2, enter amplitude 2, corresponding to the amplitude of wave 2. Similarly, enter wavelength 1 and wavelength 2 into A3 and A4 respectively. Next, fill in wave number 1 and wave number 2 in A5 and A6. Lastly, enter phase constant 1 in A7 and phase constant 2 into A8. We are now ready to choose the values for each of the parameters. To keep things simple, we will start by making the values for the parameters of wave 1 and wave 2 the same. Let's choose a starting amplitude of 1. We choose a starting wavelength of 2 units and an initial phase constant of 0. As before, we want to convert the wavelength we have already entered into the wave number. Recall that the wave number is equal to 2 times pi divided by the wavelength. Enter this equation into both B5 and B6 using the respective wavelengths. Lastly, we need to create a counter that will allow us to increment the time. In D1, enter counter, and in E1, enter equals E1 plus 0.1. This counter will increment the time so we can view a snapshot of our wave at a later time. Moreover, we need to add in the wave speed for our medium. Add the title wave speed to D2. For now, we will choose a wave speed of 1. We can now generate our waves. In the two-wave case, we will generate one wave traveling to the right and one wave traveling to the left. First, we need to enter the values for the distance. In B11, enter 0. In the row below that, enter equals B11 plus 0.05. Drag this equation down until the last distance reads 4 meters. For wave 1, we enter the cosine function we are familiar with from before, namely equals B1, the amplitude, times cosine of B5, the wave number, times B11, the distance, plus our counter E1, times the wave speed E2. At the very end, we add our phase constant, B7. This will generate a wave traveling to the left. Drag this equation down to the last entry. Let's create a graph of this wave. Click and drag your mouse over the distance and wave 1 columns. When both columns are selected, click on Insert, and then on XY Scatter, and then on Smooth Line Scatter. As before, a graph of a cosine function is created for you. If you hit F9 to recalculate the spreadsheet and increment the counter and time, you will notice that this wave is traveling to the left. Next, we want to create a wave traveling to the right. In order to generate this wave, we need to make one change to the cosine function we are so familiar with. Instead of adding the product of velocity and time, or our counter, to change the position of the wave, we will subtract this product. This will cause the wave to travel to the right as opposed to traveling to the left. In D11, enter equals B2, the amplitude, times cosine of B6, the wave number, times B11, the distance, minus our counter E1, times the wave speed E2, plus the phase constant B8. Drag this equation down to the last entry. We want to plot wave 1 and wave 2 on the same graph to better illustrate the difference between left and right moving waves. To do this, click on the graph we've already created and then right-click and choose Select Data. In this window, choose Add. We'll enter the x values first. Hit this button to select the range for the x values. In our spreadsheet, choose the distance column. Hit this button again to select them. We'll now enter the y values. Hit the button to select the range again. Now choose the wave 2 column. Hit OK, and a second cosine function will be added to our graph. Now, when you hit F9 to increment the time, both waves should move, but in opposite directions. Wave 1 in blue should move to the left, while wave 2 in red should travel to the right. Finally, we want to calculate the superposition of the two waves. The superposition is the sum of wave 1 and wave 2. In E10, enter the title Sum. In that column, enter equals C11 plus D11. Drag this equation down to the last entry. Additionally, we want to plot the superposition in our graph. We do this the same way we added wave 2. Click on the graph and then right-click and choose Select Data. In this window, choose Add. We'll add the series x values first. Hit this button to select the range. In our spreadsheet, choose the distance column again. For the y values, this time we choose the sum column. Hit OK, and the superposition will be added to our graph. Lastly, we need to fix the maximum and minimum values of the y-axis. Click on the graph, and then right-click over the y-axis, and choose Format Axis. Change the minimum to -5, and the maximum to +5. Hit F9 and observe what happens. Wave 1 and wave 2 move in opposite directions, while the superposition in green seems to stand still and go from a flat line to a sinusoidal function twice the height of wave 1 and wave 2. This is a special case of superposition called a standing wave. Notice that when wave 1 and wave 2 line up exactly, the superposition is twice the amplitude of the original waves. This is called constructive interference. When the waves are completely out of phase, the superposition is a flat line. This is called destructive interference.